Okay, let's dive into this. Welcome to this explainer, where we're going to rigorously deconstruct exactly what is happening at the bleeding edge of AI task horizons. There is just so much hype out there right now, A lot of massive claims being thrown around about what these systems can actually do over extended periods of time. But today, we're strictly following the source text to unpack the genuine breakthrough here. Because, as you'll see, the real leap isn't just about an AI spitting out longer text or running a timer for a few more hours. No, it's really all about stable coordination across time. To get to the absolute bottom of this, we're going to follow a very specific path today. First up, we'll look at this rapid shift from minutes to hours. Next, we'll break down deep dependency structures, and then explore something called the energetic paradigm. After that, we'll examine the very real, kind of scary risk of drift. And finally, we'll look at how we are actually architecting long-horizon autonomy. We are moving all the way from basic time limits right into complex systems architecture. Let's get into it.
Section 1, From Minutes to Hours, Tracking the Expansion.
So, looking at the timeline of recent AI advancements, we can clearly see this crazy progression. In March of 2024, a leading AI model could reliably knock out tasks that took a human only a few minutes. Fast forward roughly 1 year later, and newer systems could handle tasks requiring more than an hour of human work. Jump forward to the next generation, and that claimed task horizon expanded to many hours. People look at this and frequently describe it as a rapid doubling in the amount of work an AI can complete independently. They even compare it to Moore's law, basically arguing that AI capability is improving way faster than traditional computing power. But we really have to stop and ask ourselves, what exactly is doubling here? When we see these massive, sudden jumps in task horizons, what underlying capability is actually scaling up? Well, let's totally deconstruct this myth right now. The breakthrough is absolutely not simply the number of tokens a model can produce. It's not merely blowing up the size of the context window, and it is definitely not just the sheer amount of time the model remains active. The reality, the truly important change going on under the hood, is the length of the causal chain the system can sustain without losing control of the task. Think about it. A 4-minute task might only require a handful of decisions. But a 12-hour task? That involves dozens or even hundreds of dependent actions. The system has to preserve that original objective while the local conditions around it keep changing constantly. Which brings us to Section 2, Deep Dependency Structures, or the anatomy of a long task. Let's formally lock in the definition directly from our source text. Long horizon capability is the ability to maintain organized action across time. Like we just mentioned, it's all about preserving that initial objective even as the environment and the context shift around it. It isn't just about doing more stuff, it's about keeping the whole shebang perfectly aligned over an extended period. Look, if you've ever tried to get an AI to write a massive, multi-part report for you and it completely lost the plot halfway through, well, this is exactly what's failing. And this brilliantly illustrates exactly what we mean. Just think about a complex task, like managing a multi-stage media project. The system has to research the subject, draft the script, edit the audio, and finally publish it. Each stage depends incredibly heavily on the quality of the earlier stages. A mistake in the initial plan totally derails the research. Weak research ruins the script. A flawed script ruins the audio recording. By the time you hit step 4, publication, an error made way back in step 1 might be virtually impossible to track down. A longer task is not simply a larger task. It is a deeper dependency structure. This is exactly why measuring long-horizon capability just by human work time is kind of useful but ultimately incomplete. 12 hours of human work can mean a million different things. So the source text provides 6 specific dimensions we must analyze instead of just staring at a clock. We have to look at the step count and the dependency depth, meaning how many later operations require the AI to remember a previous state. We also have to look at state persistence and correction demand. How often does the system have to detect and repair its own errors over time? And finally, consider environmental change and consequence sensitivity. If new information alters the plan, how catastrophic is a single uncorrected early error to the entire final outcome? Measuring capability by a clock alone completely misses all of this nuance. It doesn't reveal how much actual intelligence is required. The real frontier here is controlled duration under dependency. Section 3. The energetic paradigm, managing finite resources. Let's look at the strict boundaries of this concept. Our source defines the energetic paradigm as a framework where a long-horizon agent continuously manages finite resources. It only has so much context, limited computation, limited memory, tools, time, and verification capacity. Because the AI literally cannot inspect every single detail equally or preserve every intermediate state with maximum precision, it has to decide where to spend these finite resources. Long-horizon reasoning is therefore largely a problem of attention governance. The system has to inherently know which decisions deserve deep, rigorous reasoning and which outputs require independent checking. And this builds into a critical realization. Access is not control. Sure, a massive context window gives a model access to way more information, but dumping 1 million tokens inside a context window absolutely does not guarantee that the system will actually identify the most important dependency. A relevant fact might be sitting right there in the data, but be functionally invisible to the AI. It might retrieve it too late, misinterpret it, or let newer, completely trivial information overwrite an earlier critical constraint. The real challenge isn't just remembering a bunch of information, it's prioritizing it. Moving to Section 4, the risk of drift, when autonomy becomes unstable. This brings us to a huge hidden danger in long-horizon tasks. Sustained intelligence requires what the text calls constraint persistence. This means preserving the authority of important information across time, not just lazily retaining it in some memory bank. For example, if you define a critical rule at the start, and hours later the system finds an easier shortcut that breaks that rule, well, the instruction might still technically exist in its memory, but if it no longer controls the action, that memory has failed operationally. And the frightening cascade of drift happens exactly like this. Longer autonomy can easily create the illusion of intelligence while hiding growing instability. The system might produce totally coherent actions and really detailed plans, but gradually shift the meaning of the task altogether. The original objective subtly becomes a simplified proxy. Then, that proxy becomes the new working objective. And finally, that working objective becomes the evaluation criterion. The system ends up succeeding brilliantly, but against a problem it has quietly redefined for itself. Each additional stage, each handoff, creates yet another opportunity to drop a constraint or distort a priority. To combat this insidious drift, the real breakthrough must include stable task identity and absolute traceability. When a long task fails, the system might hand you a beautifully polished final result that's secretly built on a massive hidden early mistake. Therefore, the system has to preserve the entire path from its initial assumptions to its final conclusions. It has to record major decisions, retain its rejected alternatives, and clearly distinguish verified facts from provisional guesses. Without this level of traceability, handing over longer autonomy to AI just produces larger, far more dangerous black boxes. Section 5. Architecting long-horizon autonomy through hierarchical control. So the crucial point is that a single reasoning process simply cannot attempt to manage every single detail for 12 hours straight. It would lose its mind. To prevent the system from losing its global direction, it needs a hierarchy. It needs a strategic layer to remember the big picture objective and a planning layer to convert that massive goal into manageable milestones. Then an execution layer handles the local, day-to-day actions, while verification, memory, and recovery layers are constantly humming in the background. They double-check results and preserve evidence so the system knows exactly when to stop, branch out, or revert to an earlier checkpoint if it realizes it took a wrong turn. When you tie all these layers together, the long-horizon task is governed by a central control structure, managing the objective, memory, verification, constraints, and recovery. What we are really looking at here is not just an increase in raw baseline model intelligence. The leap from minutes to hours is actually the emergence of a completely new systems architecture. The model is becoming just one component of a much larger machine that can actively plan, act, remember, verify, revise, and continue. And honestly, this distinction completely changes how we should be evaluating these systems. A standard benchmark might measure whether the final answer is technically correct at the end, but it won't tell you how fragile the process was getting there, or if the system actually preserved the user's true objective. A 12-hour success on a benchmark is certainly evidence of increased capability, for sure, but it is not proof of stable autonomy. True progress measurement means evaluating whether the system is actively reducing uncertainty, satisfying core constraints, and effectively completing dependencies without getting hopelessly stuck in a loop. And that brings us to the core conclusion, directly from our source text. The real breakthrough is not merely that the AI works longer. Quote, "The breakthrough is that it can preserve enough structure to make continued work meaningful." As these systems expand to handle tasks that take days or even weeks, the decisive question we have to leave you with today is this. As these horizons expand even further, can AI reliably preserve this complex structure, or will the sheer weight of the complexity simply overwhelm the objective? Thanks so much for joining me on this explainer, and keep questioning the horizon.